Hi, in this video we're going to do a geometric perpetuity example. I mentioned in the learning video that geometric perpetuities are easier actually than geometric annuities. I think you'll agree with me after you see this example. So we got a perpetuity immediate with annual payments. It has an initial payment of 12. Each subsequent payment is k% more than its preceding payment. The present value of the perpetuity is 600 using a 5% annual effective interest rate, and we're asked to determine the present value of the perpetuity using a 7% annual effective interest rate. Okay, well, let's start with the fact that the present value of the perpetuity is 600 using a 5% interest rate, and look at what the timeline is going to look like. Now, this is a present value of a perpetuity, and I'm told it's a perpetuity immediate, so the present value is one period, in this case 1 year, before the first payment. The first payment is 12. So our timeline is going to look like this. The first payment is 12. The second payment, k% is a 0.01 times k, so k% more than the preceding payment. I would need to take the payment of 12 and multiply by a 1 plus 0.01k. So that's what my payments are going to look like. First two payments are going to look like they're going to continue. The next payment that's not shown will be a 12 times a 1 plus 0.01k squared, and so forth. All right, but I don't need that. I just need the first two payments. And I've got the timeline. I need more room, so let's move that up to the top of the slide. Using an I equal 0.05, the present value of 600. Perpetuity immediate. What makes this perpetuities a little bit easier than annuities when you're dealing with these geometric things, or is that there's a two-step process instead of a three-step process. The step one is the same as step one for an annuity. You value each payment, do so at the valuation date. So I'd have the present value, the first payment of 12, have to discount for a year, and I would discount for a year by multiplying by a V or dividing by a 1.05. The second payment of 12 times a 1 plus 0.01k, I need to discount 2 years, so I would divide by a 1.05 squared. That's like multiplying by a V squared and so forth. And then that's all I need. I recognize, since this is a perpetuity, I have a geometric series now. It's a geometric series with a common ratio of 1 plus 0.01k divided by 1.05, because that's what I need to multiply the first term, the 12 divided by 1.05. I need to multiply that by the common ratio to get to the second term. So that's how you identify the R value there, the common ratio. Again, it's just a two-step process. The second step is to recognize then that the value of a geometric series is its first term divided by 1 minus the ratio. So now I just got to identify, what do I mean by the first term? What's the first term and what's the ratio? Well, the first term is the first term of the VEP expression. It's the 12 divided by 1.05. And the ratio I've already talked about. It's that R value. It's the 1 plus 0.01k divided by 1.05. So then I just plug everything in. I plug the 600 in for the present value, plug in for the first term, plug in for the common ratio, and I get this expression that I just need to solve this expression for k. It may look harder than it actually is. It's not really that hard to solve for k. What I would do is in the denominator of that complex fraction where I see the 1, I would replace that 1 by 1.05 divided by 1.05, because I'm going to add those two terms together in the denominator and get a common denominator in the denominator, add those two terms together, and let's see, I would get a 1.05. I'm subtracting 1 from that. That's going to give me a 0.05, and then I'm also subtracting the 0.01k. So I get this expression as simplifies to this. This is still a complex fraction, but now the 1.05s cancel off. I get this. Cross multiply, solve for k, and you'll get k equals 3. Now, we're not done yet. If we go back to the problem, keeping in mind that we just found that k is 3, go back to the original problem. It says we got this perpetuity immediate with annual payments, has an initial payment of 12. Each subsequent payment is k%. Now that I know k is 3, each subsequent payment is 3% more than its preceding payment. The next sentence, the present value of the perpetuity is 600 using a 5% annual effective interest rate. That's not really needed anymore. That's what I used in order to get the k value. That's the extra piece of information I needed to get the k. So now it's just determine the present value of the perpetuity using a 7% annual effective interest rate. So I got first payment of 12, next payment is 3% more than that, so it's 12 times 1.03 and so forth. I'm using a 7% interest rate. I want to know what the present value is. Again, it's a geometric perpetuity, two-step process. Step one, VEP. When I VEP at the valuation date, I get this expression I get this equation that the present value is equal to 12, this time divided by 1.07. I got to discount it for 1 year. 12.03 discounts for I got to discount it for 2 years. Multiply by a V squared, which is the same as dividing by a 1.07 squared, and so forth. That's a geometric series with a common ratio of, it should be clear, the common ratio is 1.03 divided by 1.07. Step 2 is the same. The present value is the first term divided by 1 minus the ratio. This time the first term is a 12 divided by 1.07. I've got the ratio there of 1.03 divided by 1.07. Go through whatever process you're going to go through. I'm kind of doing it the same way as before. The 1 in the denominator of that complex fraction I'm writing as a 1.07 divided by 1.07, so I can combine the two terms in the denominator to get a 0.04 divided by 1.07 in the denominator. Now I got this complex fraction, both the 1.07s cancel off, and 12 divided by 0.04 is 300. So my answer is 300. Again, these are easier problems than the geometric annuity problems. So you want to see geometric perpetuity problems on the exam. They're all done the same way with this two-step process. And so I hope you're lucky enough to see a few of these on the exam. All right, I'll see you in the next video.